he ditched that 6 or 7 years ago and replaced it with his own language called Julia.
There was an overlap period.
There was an overlap of a year or so. And Julia just won the Wilkinson Prize in numerical software, which is one of the most prestigious prizes in numerical analysis, numerical software. So it's a great pleasure to have Alan here. Please, we're interested to know what you're going to say.
Thanks, Alex. It's a great pleasure to be here. I can't remember how many times I've been to Cornell, but I think it's probably been around 4 or 5. But I don't think I've been here for like the last 10 or 15 years, so I'm certainly been due for a visit. So what I'd like to do, I really have 2 main messages, and maybe there's sort of a continuous line between them, perhaps. I want to talk about the Generalized Singular Value Decomposition, which was invented right here by Charlie Edelman. I gather Charlie can't be here right now. I would love to have seen him. But some of you may know that he's the inventor of the GSVD. And I just want to kind of see the GSVD in a new light. I think the GSVD is like the next big factorization to take off. I kind of feel like the GSVD suffered from a bad, marketing agency, and it's time for them to fire their old marketing agency and hire me maybe to push the GSVD. The end of this talk is going to be about Julia, but it's not about programming language. It's not going to be like Julia versus MATLAB or Python Mathematica. I mean, these discussions are actually kind of ridiculous, and I don't even want to start any one of them. What I would like to do is tell you why I think that the programming languages can take us beyond what we think they can do. We usually think of programming languages as taking mathematics and bringing them to life, right? I mean, that's what you write down a formula maybe on a blackboard, and then you instantiate it in the program and you can calculate. And that's what we all do, and that's fine. I'm starting to see that with Julia, we can start to do some interesting abstractions and sort of go bigger and beyond what I just said. And I don't even know if I have the right words to say it, but at least I have some examples to show it. And so there's going to be a bit of a continuity between the GSVD and this statement about programming languages, and we'll watch them unfold. So here's my outline, or something that is meant to kind of put things together. I'm going to start with the GSVD. I'm going to end with back propagation. If you look into machine learning these days, very often people say, what is back propagation, and how does it work? And, usually the standard answer involves turning the chain rule upside down, and that completely confuses everybody. It confuses me. I don't get it. And then I realized that it's just, once I realized that it's just a matter of how you multiply matrices, it's like, linear algebra. That I get, right? So that's what we're going to talk about at the end of this. But let me just start with the GSVD, okay? And so let me start with what today everybody knows, which is the SVD. Now, when I first started as a student, it was kind of interesting. The SVD was almost unheard of. I mean, unless you were friends with Gene Golub, you did not know about the singular value decomposition at all. So nowadays, we all know the use sigma be transposed. We know that a matrix A takes a unit ball into some sort of ellipsoid, and the semi-axes are the singular vectors, the lengths of the singular values, the Previous matrix, the other set of singular vectors. We all know that today. Though it's still the case that I could actually easily fool grad students. I could say, I mean, I do this all the time. I do it every year. What are the lengths of these things? Oh, they're the eigenvalues. Oh, what if the eigenvalues are negative? Oh, the absolute value of the eigenvalues. What if they're complex, right? Grad students get fooled all the time. They always still say eigenvalues. But nowadays, more and more, even the graduate students know these are the singular values. All right, we know the SVD.
Is that Golub's license plate?
That is a picture of Gene Golub's license plate. He had 2 license plates on his car at Stanford. I actually drove one of them once. He left it for me at San Francisco airport. What he didn't tell me was that it was a stick shift. He left the key. I don't know how to leave San Francisco. Yeah, so he had a Dr. SVD and a Prof. SVD license plate on his car. And, it's time somebody should get the GSVD license plate, I guess. So, yeah, but, I've watched the SVD, one subject after another fall to the SVD, right? Biology, picks up the SVD, the first few people win a prize. Economics, oh, there's this SVD, the first few people win a prize, right? One field after another fell to the SVD, and the first people won the prize. I think this can happen in the GSVD, right? If somebody here is in biology, you could be the first, or in economics, you could be the first, or the GSVD. History might be able to repeat itself. But when it comes to the GSVD, it's just not as well known, as I said at the beginning. And you want there to be like an ellipse picture. So you go online and you ask, what is there geometry for the SVD? So 19 years ago, somebody asked, is there a geometric interpretation of the GSVD? Okay, and if you look here in MATLAB Central, there's message 1 of 1, which means the silence was deafening. Right? In 19 years, nobody but nobody answered anything about the geometry of the SVD. Nowadays, you can even look at Theorem. What is the geometric interpretation of the GSVD? No answers yet, request answers. Right? And so, that's a clue that that the GSVD's geometry somehow has been waiting to be found. I love the GSVD, but if you look at the definition, you just get lost in a sea of matrices. Every time I would look at this definition, it just didn't mean anything to me. So here's the definition you'll see, that you take two matrices that have the same number of columns, you stack them on top of each other, and some of these matrices are orthogonal, some of them are diagonal. This one's non-singular, but it's not orthogonal. How dare a self-respecting SVD have a non-orthogonal or non-diagonal matrix somewhere in the picture, right? But H is simply assumed to be non-singular. Too many matrices, who knows what this all means, right? It's hard to keep track of it all. And of course, where are the ellipses? You want to know, there's no pictures, right? Like when my kids were 5 years old, if there were no pictures, forget it, right? There's no meaning to it. It has to have pictures. So you go to the documentation and software. This was the old Dr. Julia, by the way, I rewrote it now, for Julia at least, I get control over that one. Though I don't think they've accepted it yet. I still think it's just sitting in GitHub somewhere. But you look at MATLAB and Mathematica, or even this old, and you just see a repeat of what was on the previous slide. U, C, D, all these matrices, you don't know what to make of them. Go to Wikipedia, and you again see the same repeat of all of these things. There's no real meaning to this. Well, I'm going to show you the picture. And the reason why you haven't seen the picture is there's a very simple reason. The picture really starts to make sense only in 4 dimensions or higher. You could do it in 2 or 3 dimensions, but it's kind of a little bit too constraining. So I'm going to draw you a 4-dimensional picture. People think this is hard, but it's not that hard. So this is a representation of 4-dimensional space. Okay, and I'm going to imagine an example where A and B are both 2x2 matrices. This example is fairly representative of the fully general case for high-dimensional matrices. So 2x2 will be enough. So I'm going to be in 4 dimensions, and here I'm going to have the x multi-axis. If you take the first 2 columns of the identity, or if you're really cool in the machine learning world, you say the first 2 one-hot vectors, right? That's the new language of machine learning, which the old language was the first 2 columns of identity, or coordinate vectors. People say one-hot vectors are here. That's the cool language. And then here's the y multi-axis, which is the last 2 columns of identity, the span. So this is a plane, and this is a plane. Okay, and if I take this matrix on top of this matrix, I'll get a hyperplane. It'll be a 2-dimensional hyperplane somewhere in space. And so here's this 2-dimensional hyperplane. And what I would like you to do is imagine the unit ball in general, because it's a plane, it's just a unit circle. I want you to imagine the unit circle that's here, centered at the origin. It's kind of, to keep it from getting crowded, I'll just draw the segments of the unit circle. But literally, this is an entire plane, and there's a unit circle on that plane. All right, so everybody's with me? I've got the 2 multi-axes. That's just sitting there. And then I've got 2 matrices, two input matrices, A and B, and their span's going to be a hyperplane. Okay? 4-dimensional picture, no problem, right? All right. So just to make it a little bit more convenient, I'm going to explode the view. So that unit circle, which is sort of sitting down there, I'm just going to pull it out just so that we can think about it. And what I'd like to do is project it downward and leftward. Okay, so I'm going to take this unit circle, I'm going to project it downward, and I'm going to get an ellipse over here. I'm going to do leftward, and I'm going to get an ellipse over here. And I'm going to call this one the cosine ellipse, and the other one is the sine ellipse. Okay, and just like any time you have a vector and you sort of resolve it into components, like if you have a unit vector, it's going to become a cosine and sine. Every one of these are going to, the entire circle gets resolved into cosine and sine, right? And so we can call that the cosine ellipse and the sine ellipse. So here's a little bit of a picture. The colors look a little washed out. It's kind of, they were more orangey and greenish, if you can imagine. I feel like I'm sort of stuck in an old movie here, but nonetheless, Here are some directions, cosine 1 times u1, c2, u2, and here s1, v1, s2, v2, and as you'd probably expect, these are cosine sine pairs, right? So this squared plus this squared is 1, c2 squared plus s2 squared is 1. Okay? If you put these on top of each other, you get you get something that's a unit direction up in the 4-dimensional space. All right? So that's it. That's a geometric derivation of the GSVD. This is really the true meaning of the GSVD, or at least sort of a big piece of the GSVD. Now you can draw these pictures in 3 dimensions and 2 dimensions, but there's really not a lot of room. Planes end up intersecting with planes when they didn't have to in 4 dimensions and more. So really the 4 dimensions kind of captures the story. But this is what's going on. You start with 2 matrices, A and B. The U matrix that you'll get out are the semi-axes of this ellipse. The S matrix, the V matrix is the semi-axis of this ellipse. The cosines of the lengths, the sines of the lengths here. And then finally, the last matrix is just the change of basis, which basically brings you back to the columns of this matrix. So that's it. That's the entire story. And it really only depends on the span of AB until you bring in the next matrix. And so if you speak this language, this is actually just a coordinate system on something called the Grassmann manifold. This is just a coordinate system for hyperplanes in higher dimensional space. Okay, so that's a GSVD picture. It's kind of fun to have. Once you start to have this, you can start imagining doing matrix trigonometry. I feel like, in high school you learn ordinary trigonometry, but I feel like there's a matrix trigonometry where, in some sense, this is more than a length now. It's an entire matrix, say horizontally, and another matrix going vertically, and then you have a hypotenuse matrix. There are various versions of the square root here, which one is the right one to take. But ultimately, this is really what's going on. When you draw a right triangle in the plane, if you put one axis along the x-axis and one on the y, there isn't much room. I mean, I guess you could go the positive direction or the negative direction on the first base, and then I guess the second base can go up and down, but there isn't much directionality. But when you're free in the high-dimensional space, you need to specify all the directions as well as the lengths, and so that's what the u and the v will capture, and the h is the hypotenuse. And so this is really nothing other than a generalization of what people do in 2 dimensions all the time. If everything here was a scalar, I would say that an arbitrary 2 vector could be written in terms of its radius, its length, and then a unit vector cosine sine, and by the way, you need a plus or minus sign just to say what you are, right? And so this is a generalization really of ordinary trigonometry. Okay, and I don't want to spend too much more time on this, but we could talk about all the various sines and cosines and tangents and so forth, and it's all connected to this matrix trigonometry. All right, let me keep on moving though, because otherwise I'll never get through my talk. So one could think of the GSVD as a bit of a multi-slope, if you like. And so if you have an ordinary line in 2 dimensions, one way to specify it is you take a vector, which is its direction, and then you take all scalar multiples, right? And that's the graph of a line. And we call the slope b over a when a is not 0, or maybe even if a is 0, it's okay, as long as they're both not 0. Here, this is a matrix, this is a vector, so this is matrix times vector. The graph is now a hyperplane, and the GSVD is basically the multi-slope, okay? It basically, just like the slope is the tangents of the axes here, these are the tangents of the multi-axis, right? And so again, it's just an obvious generalization to matrices of things that you already know. A little bit of a warning, because sometimes people think they make a mistake. This has nothing to do with the angles between the span of A or the span of B. They don't even live in the same space. It all has to do with the angle between the span of AB and the coordinate hyperplanes. All right. I've got a couple of theorems. Let me see. I just don't want to lose all my time. But all right, let me mention some of these theorems that I just put into the paper recently. So I was hoping that this was always true, that the GSVD of AB, that's the thing on top of AB, the actual generalized singular values, would always be the SVD of A times the pseudo-inverse of B. But then I tried, at least the non-zero, the non-infinite ones. But then I took this very simple example, you could actually do this one by hand. And I saw that the SVD was 2.5, the GSVD was 2.4, there's also an infinite one. And I said, something's wrong. And then what I did was kind of fixed it by saying that you have to, there's a little bit of a technical fix, but if you project onto the orthogonal complement of the image of some null space, then it all comes out just right. Okay, so that's a little theorem. Another theorem that I'll show you is this one, which kind of makes things right again. Basically, forget about all the notation. What this is really saying in simple English is that the thing you want to be true is true in some limiting sense, as long as you have the right ranks. But it's not true in some sort of unfortunate special cases. Okay, enough with that. I want to talk about what the GSVD is for a pure mathematician. So years ago, I had these slides, and I just resurrected them. So these are slides from 2002, where I wrote, it doesn't look like it's showing up too well, but this is a long time ago at something called the Householder meeting. And I was wondering where matrix factorizations came from. Oh, that's better. Thanks. Yeah, so here's the stork bringing a matrix factorization, newborn matrix factorization. And there's this wonderful math this is me at the meeting. I'm pretty sure, I'll bet you Charlie Edelman is there. Isn't that him right there? That's it. Right there. So there's this whole stuff in LIGH algebra, and I'm not going to explain it here. I just kind of want to advertise that it's out there, that there's something called the Cartan decomposition. Maybe some of you have heard of it, or maybe not, but if you've heard of the Cartan decomposition, basically from the Cartan decomposition you get all kinds of KAK decompositions. And one of them is the singular value decomposition, another one is the CS decomposition. It's kind of nice because, like, when you study numerical linear algebra, you learn these decompositions like a laundry list. Like, first there's the SVD, then you learn the CS, maybe you learn another one, and like, they're all just sort of like separate. But through the brilliance of Cartan, and long before numerical linear algebra, some of them, not all the ones we know and love, but some of them have been unified by one grand theory of matrix factorization. So it's kind of nice to know that this exists. And I went over to one of the LIGH algebra folks in the math department at MIT, and I do this a lot. I said, I know for sure that, you know, I was wondering if you could do the GSVD with 3 matrices. And, you know, as I expected, this colleague of mine said, what's a GSVD? But I knew that there was a language in pure math for it. I mean, I do this all the time. I just like to know the language, even just to know how they call these things. So after a lot of discussion, we found out that if there was something like a GSVD with 3 matrices, it would live in this double coset space. So there's this paper, and I just kind of just show you a few words. I don't really intend for you to read this. What I want you to know is that there's GSVD-like stuff in here. So I don't know if any of you have ever looked into LIGH algebra, but what I'd like you to know is, I'm going to surmise that you haven't. I mean, if you have, more power to you, but I'm going to surmise you haven't. And I'm going to guess that this all looks unreadable and has nothing to do with anything you would ever care about, right? And of course, this is just notation in another language for everything that you might care about. And that's what's really fun here. So the clue might be that this is n by n unitary matrices, that's G. And we're going to factor these unitary matrices. And so I'll just kind of give you a little bit of a story here. What is this double coset space? Well, we're going to start with n by n unitary matrices. And the H is going to be written, you saw it on the previous slide, it's a product of unitary matrices. And all this is a block diagonal matrix, where the first one is so it's just this matrix, which is M1 by M1 and M2 by M2 and 0 and 0, right? So this is sort of a MATLAB kind of name, block diag. But it's just an orthogonal matrix up here, an orthogonal matrix here, and zeros and zeros. Okay, and then the L is going to be another such decomposition. And really, all this fancy notation means is take your orthogonal matrix and put a vertical line, which you see in all the linear algebra books, right? All the numerical linear algebra books. Put a vertical line down it, and then this one says put a horizontal line. Okay, and if you had 3 matrices, you put 2 horizontal lines. Really, so that's kind of what I'm sort of oversimplifying a little bit, but as so often happens, you read these papers, you find your way, you learn the vocabulary, and you feel so good about yourself, but they still don't have any more answers than we knew before. You get like disappointed and feel like that. I don't think they've gotten any further, but they have a nice notation for it. All right, moving right along. Applications of the GSVD. I've got a bunch of them, just to sort of, maybe, as I said, some of you may want to write a paper in some other field and maybe win a prize, I don't know, and use the GSVD. So one application that's already been out there is the use for Tikhonov regularization. And again, I think I'm going to go somewhat quickly. But here, let me just sort of put this all up here. There's a whole bunch of geometry for Tikhonov regularization that you can do with the GSVD. Roughly, the story is that when you do Tikhonov regularization, I think everybody knows what that is here, maybe. You basically, instead of solving AX equals B, or the normal equations, A transpose AX equals A transpose B, you add in a lambda L transpose L term, right? And so in the end, what you're solving is this least squares problem, right? So this is sort of like the backslash in MATLAB or Julia, right? So the ordinary backslash would just be without the unregularized case would be A backslash B, but you add the lambda L to regularize it. And if you do that, you can write this as M lambda times X0, and then this M lambda matrix takes this format here. It's a matrix that's similar to a cosine squared, and you guessed it, those cosines are the generalized singular values. And the H's are the H that comes from the GSVD, and there's sort of a nice geometric proof that I'm just going to wave my hand at right now. But this GSVD picture is kind of nice because it sort of shows you that when you regularize, all the directions reduced by exactly a cosine squared, which is kind of makes you sort of feel like you know what's happening when you regularize. Okay. There's a regularization picture that's maybe a little more fun. So as you regularize, when lambda is 0, basically the generalized singular vector directions are down in this. This is a four-dimensional picture as well. I love to draw these four-dimensional pictures because nobody does. So this two-dimensional picture here, this plane down here, and this green, they're actually orthogonal planes. So this blue surface and this green surface only intersect at a point, not a line, if you can try to imagine that. In fact, what's happening is, this is a hypersphere in 4 dimensions, and what's happening is as you move the regularization parameter lambda up, literally what's happening, if you look at these spans, right, so here's lambda 0, here's lambda moving towards 1, here lambda equals 1, lambda can go on to infinity. What's happening is you're moving up this sphere, and so as you start to look into these things, you can actually really start to understand how Tikhonov regularization works. All right, but moving on to another application. This is Orly Alter in Utah. Actually, this was the application that really made me fully understand the GSVD, I thought, for the first time. What she does is she gets these genomes and puts these into matrices. In this case, one of them was a human genome and the other was a yeast genome. But there's nothing special about human and yeast. You could have all sorts of data that you want to compare. You ask the question, to what extent are we humans similar or different from yeast, right? I mean, maybe you wake up every day wondering. So in this case, you put the genomes in a matrix, and you look at the row space, the common row space of the matrix, and the generalized singular value vector directions are the key directions, which, if you look at them one at a time, so there are these, for each generalized singular vector, you can look at how much each matrix is in one direction or another, and you can decide whether it's mostly human or mostly yeast, or equally human and yeast, or tilted, right? So you have a sliding scale, human or yeast, which you can get directly from the singular vectors, and that's what Orly does, and that's what a lot of people are kind of doing in disguise, even if they don't say so. There's another application of the GSVD, which is called blind signal separation. This was done by this paper, Hundley et al. And if, with the benefit of this geometric viewpoint, you start to realize that there's nothing special. I started by taking the first 2 columns of the identity and the second 2 columns of the identity. Maybe you thought about it like, what's so special about the identity, right? There could have been any two orthogonal hyperplanes, and of course they could be. And when you start to look at the application, you realize that they are doing exactly what I was doing. They didn't say so, they didn't have this picture in mind. But if you go back and look at the math, you realize the math is simply rotating this picture onto any two orthogonal multi-axes. Kind of that's what's going on. Basically, instead of human and yeast, they've got signal and noise, right? And they're trying to figure out, am I all signal, am I all noise, am I a mixture? You see, they start to see what's going on. Okay, I'm going to mention another application here, which is the, so every couple of years, I see ANOVA tables, the analysis of variance. I swear I never understand them. I'm just me, I don't know. You know, there's all these degrees of freedom and, you know, whatever, I don't know, I just don't get it. But actually, there was an example in Wikipedia. I'll actually show you the example. I mean, you can look at it for yourself. But you can look at, you know, here, if you go to ANOVA, or, you know, one-way analysis of variance, you go towards the end, there's a computation of this thing. Right? You know, all these numbers being calculated, blah, blah, blah. Whatever you do, you end up with 9.3. Okay, and so let me just show you that it's actually just basically a GSVD. So this is the data that I just copied out of the Wikipedia article. It's exactly the same data that was from the article. And then this is a little bit of really almost too fancy Julia, but I can't resist showing it to you. If you want to create this indicator matrix where the first 6 variables are, you know, part of group 1, you know, so the second is part of group 2, and the third is group 3. One quick way to make this in Julia is this command here. B is basically saying I want to test whether the mean of group 1 equals the mean of group 3, or the mean of group 2 equals the mean of group 3. This is what statisticians do. Well, here's the GSVD. Just compute the singular vectors, and then you start projecting, and you get this very 9.3 that you saw in the Wikipedia article. So here it is without these crazy tables. Maybe overkill, but I just wanted to show you that the GSVD even calculates these things.
Sorry, what is the meaning of the 9.3?
The 9.3 is so in the ANOVA language, it's the F statistics, which you then compare. If it's what's the story? If F is big or little, I can't remember anymore. If it's too big or too little, with some confidence, the means are equal or unequal. And, you know, I don't remember. Who knows what I'm saying? but it's not.
There's only one vector, so what means are you comparing?
No, there's you've got. This is the data. I'm going to teach it over here real fast. The data is I don't know. I don't even speak statistics, but you did something and you got 6, 8, 4, 5, and 3, and you call that group 1. Okay, and then you have 4, 8, 12, and 9. You call or something like that. I don't know, or whatever, something like that, and. Or, sorry, it's the first 6. 6, 8, 4, 5, 3, 4 is group 1, 8, 12, 9, 11 is group 2, something like that. And the last 6 is group 3. And you want to say with what confidence is the mean of the first equals the mean of the second, and the mean of the second equals the mean of the mean of the first equals the mean of the third, or the mean of the second. They're all equal. They're all the means are equal. Anyway, look up ANOVA. I don't really care. But it's one of those things. The GSVD calculates it. It calculates the F statistic. And then, yeah, depending on how big this number is, you can say with some confidence that these means are equal or not. Okay. Let me move over to something that's a lot more fun for me, somewhere in the matrix theory. So going from the ANOVA to the MANOVA, that's the multivariate analysis of variance. If you look into the world of random matrix theory, which by the way is starting to get, it was always like a fun little hobby for me, but now the machine learning people are sort of discovering random matrix theory. It's kind of fun to watch them do that. And so it's kind of getting sort of more popular than ever these days. But in any event, there's something called the Jacobi ensemble, where if you take a matrix of standard normals, and so this is sort of MATLAB or Julia speak for a matrix of mean 0, variance 1, you know, independent elements that are M1 by n, and similarly by M2 by n. If you form this matrix, or this metric form this matrix and compute the eigenvalues, this is called the Jacobi ensemble. And of course, this is really a lot of crazy notation for the GSVD. In fact, here's sort of the clue. If somebody's in another field and you want to, if you ever wanted a clue that there's an SVD, you look for the A transpose A's. That's the giveaway. If there's an A transpose A in your life, you remove it and you put the SVD in, right? And then you look like a hero, right? If you see two matrices A transpose A and the B transpose B, that's the clue for the GSVD. That's the clue that you could be the new hero by sticking the GSVD in your life and then removing all that old-fashioned notation and looking like you're really, modern with the GSVD notation. So this is the sort of oldish notation. These are the eigenvalues are basically sort of the squares of the generalized singular values. And I'll just put this right here, that these are the cosine squares of the eigenvalues. And if you're into this sort of thing, you could actually calculate the Jacobian of the transformation from the matrices to the singular values and singular vectors. And so I've got a little slide here. I'm not going to sort of explain it right now. But it's sort of, there's something very interesting. If you want to do things like differentiate the SVD, differentiate eigenvalue decompositions, and here I am differentiating generalized singular value decompositions, the math is doable. It's a little bit hairy, but you can get analytic formulas. Or, nowadays, you could just let a computer do it for you. And it's sort of a miracle that you could do that. So I worked really hard. I really like to do these sorts of things. And I actually literally got the Jacobian for the GSVD. And here's sort of the formula. Because I'm in an orthogonal space, I have to sort of wedge the directions together. But basically, the key part of the formula for the GSVD Jacobian is here. So just so you understand what's going on, every matrix factorization is really a change of variables. I mean, maybe you know LU, right? LU takes an n by n matrix, and it turns it into the n times n minus 1 over 2 parameters in L, and the n times n plus 1 over 2 parameters in U. Right? It's just a change of variables. It's n squared going in, n squared going out. All right? So is the SVD, so is QR, so is the GSVD. If you have a change of variables, there's a Jacobian determinant somewhere to be found. Maybe you think that it's hopeless to try to calculate it, or maybe you'll believe me if I tell you you can do it. And the mathematical gods are kind. You actually can, in almost all cases, you can calculate these things on a blackboard. And here is the answer. It's hard to do, but it can be done. But I'm very intrigued, and to show you that this sort of thing can actually be calculated even more readily, numerically, with if you have a differentiable programming language. And so here I have a Julia code, which I just copied over the formula that was on the previous slide, and I included the H as well, the determinant of H. And I sort of found this a very interesting exercise, because these days, people want to differentiate programs left and right? So this is a machine learning application. So the differentiable programs are all the rage. It makes you wonder, like, you go back and look at calculus classes, and you see that the students sort of doing calculus by hand, and then you see these computers numerically differentiating things that are really, really complicated. And these are not symbolic derivatives. They're not like finite differences like you learn in numerical analysis courses. It's some other something, right? It's this other thing that I'm not going to explain here, but it's not the two things you think it is. And that's a very interesting thing. And so I actually talked to various people about doing differentiable programs before Julia, and people were saying that, yeah, we can, like, I want to do the SVD. And they told me, yeah, we can teach our system to differentiate the SVD. I said, teach the system? I want it automatic. What if I now want the GSVD? Do I have to teach that too? Or I want to teach, and like, no. And then I started to understand where it is where the difference between having a computer do the thing you ask it to do and having a computer system that can do very, very general things. There's a difference between being able to differentiate an SVD but not the GSVD, or to be able to differentiate any program that could be put into the computer. The second thing is way more powerful than the first. And here I thought I'd just show you it happening for the GSVD. So here I'm basically doing a sort of poor man's GSVD computation. So this is a little function for the GSVD. And what I'm going to do is use the automatic differentiation formula, the package that comes with Julia. So these days, lots of people have automatic differentiation packages to differentiate everything and everything. And so I basically computed them, and then I stacked it all up, and I get the Jacobian, which is the absolute value of the determinant. And I also use the exact formula. You might recognize, even if you don't speak Julia, you might see, here's the absolute value determinant of H to the power m1 plus m2 minus n, right, that's this part, times the product of the cosine squareds, right, that's this part, and then there's the cosines to the ends. Maybe you could recognize that this is the analytic formula, and you can see that it gives the same answer. I could run it again if you think I'm cheating. I'll do a bunch of different random matrices. I don't know how big am I doing this. You know, here's a different answer, and you can see this is one of them is this is this is the automatic differentiation, and this is the analytic formula. So even though it's kind of fun that you can get an exact answer analytically, it's really remarkable what computers can calculate as well numerically. It kind of boggles the mind sometimes just how far computers have come to be able to calculate.
Trust one of those two more than the other for the last 2 years.
Oh, well, you know, it's yeah. I don't know. The last digits, it's,
That's 3.
no, that's, yeah, I don't, which one would I bet on? That's a good question. I guess I don't care. I have a numerical analysis training. I don't think this matters. So, but, I mean, these are floating point numbers going in, so already it's fluffy, right? I could say more, I could even say better, but I won't. Yeah. So back to sort of my main story. All right, so you saw the GSVD Jacobian. One of the things that with Julia I keep looking for is just how far can we go with abstractions. As I said, of course a computer language can implement a formula. I mean, that's what everybody does. That you know, that's not interesting. You know, maybe when people say just programming, that's what they mean. But I'm really very interested in the sorts of things where if you've got the kinds of abstractions that we know and love in mathematics, we can make them actually available on the computer. All right, and this is sort of vague, and even I'm having trouble saying this. You probably don't even know what I'm talking about. So what I'm going to do is at least give you one example that might kind of show this off, so see if I can kind of get the idea out. At some point I'm going to be able to say this more clearly, but I have a feeling I'm still 6 months off. But the example might make it work. So there's something out there, and again, maybe if you're getting into the machine learning world, you start to see it. It's called reverse mode automatic differentiation. So there's 2 flavors of automatic differentiation, neither of which is symbolic and neither of which is finite differences. There's the forward mode and there's the reverse mode. Okay, and the reverse mode is a lot more popular these days because if you have these big deep neural networks, usually you have many inputs going in and a few outputs, and so the reverse mode is somehow the efficient one when you have many inputs and few outputs. So you have lots of data, you know, images that you're training, and you just want to recognize whether it's an apple or an orange. So you have many inputs and few outputs. This isn't the real world very often, but if it was the other way around, then forward mode would be favored. And if you get into this world, you see all these graphs, and I just, like I said, I can't follow these things. I just don't understand. I don't speak this language, right? So, but this is what you see when people talk about these things. So I have to put everything into the language of linear algebra before I can understand it. It's just who I am. You know, if there's no matrix, I don't get it. So, what is a neural network? Well, if you haven't seen it, if you've been under a rock or something, let me first start with a scalar neural network, something that nobody would ever use. Okay? What you do is you start out in the scalar neural network, and I'm not even going to do the offsets. So the parameters of the neural network are just going to be these numbers W. Okay, here's some parameters, these W's. These are just scalars right now for starters. Okay, and what we're going to do is we're going to start with any x1 you like. Okay, and what we're going to do is we're going to calculate one by one the next set of x's by multiplying by wi and then applying some nonlinear function. Right, so this could be a hyperbolic tangent, or it could just be this value if it's positive and 0 if it's negative. That's pretty popular. But anyway, h is any. Let's just say h is a differentiable function for now, though. Right, any differentiable function at all. Okay, and then ultimately we have a target value over here, and then we have the loss function, which is usually just the difference between the target value and the value you get squared. Okay, and one way or another, we would like to get the derivative of this thing, or ultimately it's going to be a gradient. All right, well, I'm going to put this in linear algebra language. So all we're doing is this computation here. Xi plus 1, now we're just scalars for now, is hi of wi xi. So let's take the derivative. Okay, so if I take the differential of xi plus 1, I'm going to have the derivative of hi evaluated here, times whatever my change to w is and whatever my change to x is. All right, so that's how you take differentials. Okay, and like I said, I've got to put it in a matrix to understand what's going on. All right, and so here we go. I'm going to put these equations here into this matrix form. So for every dx, there's an h prime xi that gets multiplied by the dwi, and then there's also an h prime w, which kind of offset by 1 gets multiplied by the dx. Okay, and so in matrix language, this dx is this diagonal matrix times the differentials of the parameters plus this lower triangular matrix times the differential of the variables in the neural network. Okay, and so we could do what any linear algebra person would do, which is basically move things around and then recognize D is diagonal right now, so this transpose doesn't even mean anything. But ultimately, if you're interested in the last one, this derivative is just, you combine these things, you get I minus L, you can transpose it if you like, and then multiply it by the n plus first column of the identity, and that's basically what's being calculated. And I can tell you right now that the difference between doing this in forward mode and backwards mode is now equivalent to the linear algebra thing of the forward mode would be take this diagonal matrix and then multiply it by this, and then pluck out the last element. But we all know through associativity that you can solve this triangular system and then multiply by the diagonal matrix, and that would of course be a better thing to do. So this is back propagation in the language of linear algebra, and this would be forward propagation in the language of linear algebra. Now, taking this one step further to be closer to the real problems, nobody does this with scalars. Okay, what we actually do is we have matrices as our parameters. Right? So instead of, now that's the capital W now, these are no longer scalars, these are matrices. And the x, the inputs, are vectors now. Okay, so what we're going to do is we're going to multiply W times x, make it a times vector, and then we're going to apply a nonlinear function to each element. Okay, so, and again, you want to differentiate this loss function somehow. And so the question is, how can we use linear algebra to write this? All right, so let's make sure everybody's following me. All right, the neural network takes as an input x1, does all these matrix vector multiplies, then does this nonlinear function on each element, all right, and then propagates forward. If I take the differential, I get this derivative of this vector element by element. This is sort of the Hadamard product with the dot times. These are the differentials of the matrices, right? And here's the differentials of the vectors. So I would like to write this in matrix language. And interestingly enough, you can, right? You can write this in matrix language, and once again, you can end up with something that looks just the same as in the scalars. But you need a notation for this. You need some operators. And the operators that we need, they're very simple linear operators. They could be written as big block matrices, but I don't think they should. So in the scalar case, if you look really closely, you'll see that the operations we did were scalar times x times scalar, scalar times x kind of again. When we went to the matrices, what we need is, we need these linear transformations where if I input an x, I left multiply by w. Or if I input an x, I right multiply by w. Or if I input x, I do the Hadamard or element minus times product of w. Okay? With that notation, so if you know what a Kronecker product is, these two work well with Kronecker products, but this one kind of doesn't quite cut it, and so the Kronecker product doesn't quite work for me. I guess that's another one that Charlie Van Loon really liked, so he probably be disappointed. But in any event, in this notation, the perturbation to the I plus first vector can now be written as this composition times dxi, and this composition times the perturbation of the parameters. And so you see what we can do is write the same kind of thing, but we have to put these operators now inside these matrices. Okay? So it's the very same thing. It's the very same linear algebra, but instead of numbers, we put operators, right? And then when we apply these operators, through, we get the right answers. Okay? And so ultimately, this is still the same kind of matrix equation. And so you kind of feel that you should still be able to work this sort of thing through with a triangular solve. Okay? So now the question is, suppose you've done this. Suppose you've moved this to this side, you've got your I minus L dx, and you want to invert that against d and get the right answer. Does your software let you do that, or do you have to write new software? You see, I, as a human, understand the abstraction of triangular matrices. For me, I'm kind of cool about putting, but I don't care if it's a number or if it's an operator. I mean, to me, a matrix, you could put an element of any ring in there and probably be happy, right? I was a good student of abstract algebra. I said, you can put anything in there. But if your software restricts you, then your software is no longer, your software is making you sort of work in the one-off mode and not in the abstraction mode. So here's the cool thing in Julia. Julia lets you just do this. And so I want to show you that I just took here's the scale. First of all, here's the scalar neural network going through. This is just pushing through the network. And I can show you.
Is there any issue when H is not differentiable?
I'm sure. Who cares?
No, but that's the typical case now used.
Yeah, the real truth is differentiability is overrated. So what's going on in machine learning these days, as you're asking. So
I was asking for your software, for your.
Oh, I don't know. Yeah, I don't know. I don't know where. It's a good question, and I just don't know the answer. But what I will tell you is, for practical problems these days, like people, the function that's sort of 0 if you're negative, and me if I'm positive. In the past, people replaced that with the sigmoid function because that was differentiable. They thought that like you're a bad boy or girl if you had a non-differentiable function. And nowadays, like the practical people don't care. They throw it away. They use this thing, and things just seem to work. And nobody asks that question anymore. That doesn't mean it's wrong to ask. But there is this sort of cavalier approach that, like, if it works, don't ask questions. I don't know if that's right or wrong. I'm just telling you what's happening out there.
I was really asking for your H prime in that case using a rectified linear unit.
Yeah,
you have to tell it what.
I think probably you're right. I have no doubt that probably you would have to do that. But anyway, getting to my point, I'm sure there are lots of things lurking that are problem. I mean, you're right to ask. Probably need you to tell me all the things I should worry about. But what I really want to draw your attention to is that here's the scalar case. I basically put these. I basically loaded up the L with the bidiagonal matrix. Here's D being loaded up with the diagonal. In this case, I also did the offsets. So I allowed the function to go Wx plus B, loading the bidiagonal with Wx. But in the end, I just go D transpose I minus L transpose \G. And I did this with finite differences and with the backslash. And here it is with finite differences, here it is with the backslash, and you could see that I get the same answers. But now the really fun part, which is doing it with a matrix neural network. And so there's a bunch of things to define, but it's kind of fun to see these. So let me show you how we do this in Julia. So I'm going to define some operators, and it turns out that you've got to define the operator and its adjoint for these things to really work very well. So you have to figure out what's the adjoint of let multiplied by A, and it takes a little bit of thought, but you can check that let multiplied by A transpose. Or you get the adjoint of the right multiplied by A, and so here's the right, and then here's its adjoint. If you do the Hadamard or the element-wise multiply, it's actually a diagonal matrix in some big space. It's its own adjoint, and somewhere we have some code that says that you could just will copy itself if you don't give it one thing. Here's the 0 operator, which is take a matrix, here's the 0, here's the identity. So these are sort of like the most basic things you'd imagine having to define. Okay, here's multiply, minus, and composition. Just some of the basic things you would need. And to make a long story short, you define all the things that you'd expect to have. Here I'm putting these parameters through a neural network. And to make a long story short, it's basically a backslash. And it gives the answer without any extra fuss. So this is with finite differences. This is with the backslash. And I didn't have to rewrite backslash. Backslash was built in generically in Julia. And so there's a couple of points to be made here by doing this sort of thing. One is a pedagogical point about back propagation. If you want to teach back propagation this way, you could first teach how do you do backward elimination with an upper triangular matrix. And then you can sort of like do what we love to do in math, which is to, we can basically put everything into the, it's now a black box, so you don't have to like explain it while you're doing the back propagation, right? You just like set up the equations and solve now, which is kind of nice to see. But the other is the point about having a software language which allows abstractions to grow with your needs. Okay, and this is not about Julia or Python or MATLAB or whatever. This is about what we want computers to be able to do for us, right? And right now, Julia is sort of a very nice language for being able to sort of explore these kinds of abstractions. I'd like to see more of them. I'll show you a couple of more that are out there, and then I'll sort of come to an end. But so here's something in the linear algebra world that Jim Damel and Jack Tungaro wrote about sort of the goal of the LAPACK package, the linear algebra package. So, or probably they wrote this at the time of Scalar pack coming around. But if this was the goal of the linear algebra package, I believe they wrote this at the time to talk about how hard it would be to solve linear algebra on computers. How much manpower would be needed, I think, was the point, because they talked about for all linear algebra problems, for all matrix types, and for all data types, and for all machine architectures and communication qualities, provide the best algorithm available, and best might mean by performance or accuracy or who knows what other measure you can come up with. And they would show these things as a, think about all the manpower that would be needed to be able to solve, this combinatorial explosion of possibilities. I mean, it seemed like a good way to get grant money because look at all the work we have to do or something. But what we in the Julia world are saying that these are all abstractions, and so what we really want to do is write the code properly. So I mean, there's some research problems here still. I don't want to say this is all solved, but what we're trying to do, and especially in the world of machine architectures with parallel computers and GPUs and now TPUs, we're trying to make it that you can still. This has sort of always been the dream of parallel computing, and we're working on it with Julia. We're trying to make it that you can kind of, just the same way you don't rewrite upper triangular solve because you have operators, we don't want you to rewrite code because you have a parallel computer. We want to make people never have to know MPI or CUDA or whatever, however you do TPUs, right? We want these things to go away if we can. We're not there by any means, but this is sort of where we're going because we see these all as abstractions. Right, and so we believe that it ought to be possible to do these sorts of things. And I'll give one last example of an abstraction that's a bit of a simpler example, but just in case that, just to kind of nail down the message, just like one of my last slides. We have lots of ODE solvers in Julia, a lot of differential equation solvers. Christian Kakis is sort of the world's expert now in ODE solvers. He's got like all sorts of stories where he compares, he probably truly has got the best ODE solvers that exist now because he's actually done the work of comparing every possible ODE solver that ever exists. So here's a simple pendulum that's being solved. But now here's the question. You write a differential equation solver, you run it through, that's fine. Now you want error bars. Do you rewrite the solver for error bars? Well, no. You just simply have a new type, which is an error bar going in. Here's your gravitational constants known to 2 decimals. And you just define the operations, but never rewrite the differential equation solver, and then out comes an answer differential equation, but with error bars now. All right. So this is the sort of thing that we see people doing in Julia all the time, where you write a problem, something for some purpose, and you have no intention at all of doing it for some other purpose. You solve it. You have a triangular solver, but you were just thinking real numbers, or differential equation solver, you were just thinking of scalars. And someone comes along and says, "I want operators. I want error bars." It actually, you want your software to still just work. Just the same way your brain thinks about it is just doing the same sort of thing. And that's kind of what we're doing in the Julia world, and this is what people mean by...
Would that work if G was plus or minus and uncorrelated all the way through? Like if you get exponential growth in the
maybe it would blow up, I don't know. I mean, I don't know what could happen. I mean, that's, you'd have to do the experiment. But I mean,
that will code in there?
The point is the code would work. What happens next is, like anything in this software, who knows? But, I mean, So there's this fellow, Dave Sanders, who's made a career of doing interval arithmetic. People sort of dismissed interval arithmetic a long time ago. But nowadays, people are starting to sort of see that it may be better than they used to think. So in interval arithmetic, you feed intervals rather than numbers, and then when a computation happens, you're guaranteed that your answer is in that interval. And so you kind of, it's one way of maybe counteracting floating points. The problem has always been that it's often too slow, or you would get it, like you'd worry about infinity minus infinity, and that doesn't tell you much. And that can happen. But Sanders has done a great job at basically taking lots of Julia code, sticking intervals in, and getting good answers, sometimes out. But you never know.
These error bars in the sense of interval arithmetic.
This is actually a little bit different because it's going to be of these, but it's kind of similar. It's kind of similar. All right, so that I'm going to kind of end here because this is my last slide anyway, and it's 4:28 according to the clock here. So yeah, so just hope I managed to. The GSVD is really great. I hope you know. I wish you probably were here to hear that, but if you anyway see some television, I love the GSVD, and just to show you that I kind of weaved a story about automatically differentiating things like the GSVD, and then you see that automatic differentiation and just how far you can go if you can systematize mathematics. I still think that we teach undergraduates sort of the how-to at the atomic level, and yet we sort of really want our computers to do things at sort of the holistic level. And I think there's something to be done here, but maybe I don't know exactly what. All right, anyway, thanks very much.
Okay, thank you very much. Are there any questions?
Yep.
So I could imagine one problem being put in, abstractions of some new higher level out into your machinery, and it works, but it takes 8 times as long. And
Good question.
It's
So
locked down multiple series.
we worry, we built Julia so that it would not. Okay, and that's the, so there's, so there, one of the co-founders of the Julia language, Stefan Kropinski, loves to say that for most languages before Julia, you could have fast, easy, generic, pick 2, right? So any 2, there are 3 ways of picking 2. But Julia was designed to be able to do all 3. So you could do fast, easy, and generic, and it just. So Julia will compile the code with the JIT just in time, and it will run fast. It will not be slowed down. That's part of the magic. It's hard to explain how that happens, but
Yeah, it's a bold pronouncement.
that's a lecture by itself. But that is part of Julia's magic, that it is fast.
I guess bothered a little bit about your comment about worrying about whether things are smooth or not worrying about whether things are
Well,
smooth.
you should be, actually. I almost said that for a fact, so you should be.
In that, I think my experience has been that if you try to take shortcuts with that, then you frequently end up with answers that look rather nonsensical.
So the truth is there is a context to my answer, which is in the machine learning world, what people are trying to do is not like calculate something to 20 digits. They're trying to, with some high probability, decide whether an image is an apple or an arm.
Yeah.
So the very nature of the problem already starts out a little fuzzy.
But the last part of my question was, do you think you can teach Julia to recognize when that happens?
I'm still trying to figure out how to teach my kids to be afraid of things they should be afraid of. Before I teach Julia to learn to be afraid of things they really ought to be afraid of. But, like getting run over by cars and things. But with all that's happening in the AI world, sure, right? It would be great. Good question. Love to see what are the sorts of things that one should be truly worrying about.
Okay, any more questions? Okay, let's thank Alan again.